want to point out before I start any of this that I've taken most of the content here from course notes that I studied from when I was studying at Simon Fraser University during my master's degree. So a lot of this is the work of Dr. Michael Monaghan, who is my master's supervisor. However, I added more stuff. So I don't want to say that it's all his work, because if there's mistakes, that's my fault. Right? So all the stuff that's here that's good and correct, it's from my supervisor. Anything that's wrong is probably my fault. So I'm just giving attribution where attribution is due. And most of the Julia code was provided by Yanni. I'm not the best at Julia. I was supposed to learn it, but I have a newborn son, so life happens. So I know a little bit, but I'm not really sort of that deep into it. But in any case, I know enough that we're going to be able to interpret these things together. So just a note, the code that I'm going to be using for this lesson is on the GitHub. You've downloaded it. So I'm just going to hopefully boot it in. And since Yanni's here, you can tell me what this means. I thought this would be working. It's not one thing, it's another. I may not have pulled from the Git. All right, bear with me. No, it's there. This was working in my office 2 minutes ago. Restart and run again, okay? Stop. Go. Reload. Okay, let's try again. Yanni, help me. No, reset the kernel. Okay. Okay, great. That seemed to have loaded everything. So a lot of this stuff I may just go over very surface level, because we talked in detail about what symbolic computation is, some of the standard examples between numerical and symbolic computation. So just a reminder, like, computing exactly means we're not going to touch floats. We're going to really limit ourselves to integer arithmetic. And furthermore, integer arithmetic that is like arbitrarily large integer arithmetic. So you may have to use this big int. But again, in order to avoid having to use arbitrarily large integers, we're going to restrict ourselves to working in what I call, and what number theorists call, a residue class, which is what we're going to be talking about. So here's all the number theory that you're going to have to sort of know in order for the symbolic polynomial arithmetic to make sense. So if some of this may be new, some of this may be old, but in any case, it's just so we can all be on the same page about how we talk about things. So here's your preliminaries. Is that big enough for you guys? Presentation mode, that's better. Okay, so I just let n be the set of natural numbers which include 0. Oddly enough, this seems to be a cultural thing. What would you guys say the natural numbers include 0 or start at 1? I say the natural numbers start at 0. I call the whole numbers starting at 1. So we're going to be working with new objects, and these objects are going to have arithmetic defined over them. Now, in algebra, we define all of the properties that arithmetic over objects have to satisfy. Right? In order to have a useful arithmetic, addition has to satisfy a bunch of rules. So in a ring, so do you guys know what a group is? Okay, so again, a group is just a sort of set of objects for which we've defined addition, and addition has to have some properties. A ring is a group that, in addition to having addition, has multiplication. And we call a ring a set with addition and multiplication, and these are the ring axioms. So it has to be an abelian group. That means the addition operator has to be commutative. There has to be something called the additive identity. So if you give me 2, there has to be something which is technically minus 2, even though it doesn't have to be minus 2. If you're working mod 7, for example, 5 plus 2 equals 0. So thereby 2 and 5 would be the additive inverses of one another. There has to be an additive identity. This essentially means we have to have an additive 0. And there has to be a multiplicative, there has to be an associative multiplication. So that is, if you have A times B times C, it doesn't matter how you bracket that, you're going to get the same result each time. And like the addition operator, we also need a multiplicative identity. So we need something in the group, in the ring, that's acting like the unit, right? So we need some element from the ring such that A times B is B times A is A. So in this case, B would be the unit. Additionally, we need multiplication to distribute in the manner that we would expect it to distribute. So A times B plus C is going to be A times B plus A times C. B plus C times A is B times A plus C times A. Now, this may seem obvious, but we're going to have to make polynomial arithmetic abide by these rules. And in that context, it may be less obvious. But just keep this in mind, right? We need to introduce a new set of objects to the system for which we're going to define a bunch of operations. And these operations are going to have to satisfy multiple mathematical properties in order to be useful. Okay, so we have rings. Those are groups with multiplication and addition. If in the ring every element has a multiplicative inverse, this ring is something we call a field. Can anyone give me an example of a field? Yes, sir. Real numbers. I'm not sure, actually. No, they have to be a field, don't they? Is there one easier than the real numbers? Well, how about the fractions? Fractions are surely, that's not what you meant by the reals, right? No. Yeah, I'm unsure what happens with stuff like pi and stuff like that, but certainly the rational numbers, right? What's the inverse of A over B? Well, it's B over A, right? Provided that the denominator wasn't 0. So since we're going to be dividing stuff, we need to be working in a field, right? You can't have division unless you're in a field. Sometimes you can get lucky, right? So if you have the integers and you have the number 4 and the number 2, it just happens that 4 divided by 2 is 2. That's a division operation that's happening in the integers, but you're just lucky. If I swap that, if I do 2 divided by 4, right, now you have 1/2 that's not in the integers. So the integers can't be a field. Okay, so one way to get a field would be to use the rational numbers, but I want to avoid using the rational numbers. So we're going to introduce a different type of field, and that is a residue class, which we'll get to eventually. There's just some other things that I want to define sort of explicitly. You may not have had to think about this, but division is not defined by its, oh, great. I think the solution for this last time was I switch ports. Let's see. Sorry, chat, we're just having some technical issues. Great. Can you still hear me, chat? Okay, great. Where was I? Oh, so you learned about division, and then they show you this long division algorithm. It's sort of inverted, right? Because the long division algorithm, like, is division, right? It's sort of like, I don't know what comes first, the chicken or the egg, but there's a theorem called the division algorithm theorem that says if you give me 2 integers, there is a unique quotient and remainder satisfying A is equal to B times Q plus R, if we say that R has to be less than the absolute value of Q. So if you do like 17 divided by 4, that's going to be 4 times 4 plus 1, right? Quotient 4, remainder 1. So this is pretty simple stuff on integers, but we're going to be moving from integers to polynomials, but doing sort of the exact same thing. So in order to prove that theorem, right, that there exist 2 integers with this property, the proof is the division algorithm. And so this is what I was talking about last week when I say I was from constructional mathematics. So if I just write the division algorithm, that serves for the proof like this. But let's just go through Julia and see that it can already sort of do some of these computations right out of the gate. So here's an example. A is 23, B is 7. What happens if we take A divided by B? That's going to show 3. Right, so what you have to understand about this division is that it's giving you the quotient. Maybe it's more appropriately called the quotient. And the percent or the modulo operator, another way of thinking about that is that it's returning you the remainder. We can just go ahead and implement the division algorithm. It's quite simple. So this is a really neat way of saying if a is less than 0, then return this. If a is less than b, then return that. Just like a neat, since the AND operator short circuits, that's like a neat little shortcut to do like an inline if statement. Otherwise, you do this. So it's just, right, these 3 lines define division, and then you can use those 3 lines and the recurrence relation therein to prove actually this case. It's an informative exercise. We're not going to do many proofs. I don't think we're going to do much proofs at all. So I can just show you that that division algorithm works. So before we hit enter, we should sort of ask ourselves what this should be. How many times does 7 go into 23? I think 3 times. And then it has remainder 2, so that's what that is. This is the built-in remainder, which acts the same way as this. This is the modulus, which acts the same as remainder. And then we're just confirming that the division property holds. We can do more remainders. What? Remainder not defined, because I have to do this. Right, just to show you that things are working. So 5 goes into 15 evenly. That's why we got a 0 remainder. How many times does 4 go into 101? I don't know, but once you do it as many times as you can, there's 4 left over. How many times does 4 go into 125? I don't know, but once you do that, there's a remainder 1. Okay, so we can also get the quotient. So this is just the same as this, essentially, except we're calculating the quotient instead of remainder. We're, in fact, going to need both. So how many times does 5 go into 15? Well, 3 times. How many times does 101 go into 4? 0 times. That's how we had the remainder of 4. How many times does 4 go into 125? 31 times. Right? So we have a remainder algorithm and a quotient algorithm. I'm just going to go here to sort of confirm the statement. I'm saying we're finding for a divided by b, we're producing q in r such that a is equal to b times q plus r. And that's what these lines are just confirming. Right? So in each case, there's this sort of nice invariant over here. And then in each case, it triggers true. Like, this seems a little bit trivial, but like we're going to draw a bunch of analogies from here to polynomial arithmetic. Right? So when you're working with polynomials and you're doing arithmetic on them, right, always try to have it in the back of your mind that you're sort of just doing the same thing that you do on integers, like on a different type of object. Okay, so in Julia, we have the percent and division for remainder and quotients on integers, so you can use that. For those of you from Python, you may be shocked to find that in Julia, if you use the double, whoops, I'm not supposed to double click that. In Julia, if you use the double division, in Python, this is integer division, and in Julia, actually, it gives you a rational type. So we do have rationals in the system. We're just pretending they don't exist to simplify our presentation a little bit. You can think of the integer division as being the floor of sort of regular division. But again, right, this is a fraction in the system. That's why it's printing out like that. Okay, so we have remainder, we have quotient, that's stuff that we should have learned from elementary school. Okay, so let's start ramping this up, because now I want to leave the world of integers and talk about sort of more specific classes of numbers that like aren't all the integers, but a finite many of those integers. So we have this special notation, sort of z sub n, and this denotes all the numbers from 0 through n minus 1. This ring is called a residue class, right? So obviously this is a ring, right? Because you can do multiplications and stay inside. I just have to always do remainders mod n, right? So suppose Zn was like 0 through 6. That's sort of all the numbers mod 7. If you do 6 times 2, that's 12. That's seemingly outside of the class. But if you take 12 mod 7, it becomes 5, and that's inside again, right? So if we have the numbers 0 is there and 1 is there. So we have our multiplicative 0, additive 0, and multiplicative identity, right? So indeed, this is a ring because it satisfies all the ring axioms. Okay, so it's critically important that we understand this statement, right? This mod operator. Have you used this mod operator in algebra or something like that? Great. It's almost identical to like putting in a % sign. So you may notice that I'm using this like triple equals now. So we have to be a little bit careful. 11 plus 3 is not equal to 2. It's inappropriate to say that. What I can say is that 11 plus 3 is equivalent or congruent to 2 mod 12. Right, so this is just a special symbol for denoting a weaker type of equality over an equivalence class. Right, so on the clock, 12 o'clock is the same as 24 o'clock, is the same as 36 o'clock, is the same as 48 o'clock. Those numbers individually aren't equal, but they are equivalent, right? So there is a small difference between equality and equivalence. So this triple equal we read as congruent to. So I can say 3 hours past 11 is 2 o'clock. Right? So 11 plus 3 is congruent to 2 mod 12. Right? That's how I'm going to express that arithmetic statement. So we can say, right, A is congruent to B mod C when A is congruent to B modulo C, which means this. So A is congruent to B mod C if and only if the remainder of A by C is B, if and only if A mod C is B, right? So those are all the equivalent statements. So you can pick one. But essentially, when you see mod, you have to think remainder, right? This is going to be sort of the number on the left and its remainder mod 12 on the right. So you've already seen overflow, right? In some of the past lectures, we talked about having a finite many amount of bits to store our numbers. So going sort of 4 over 253. So 253 plus 4. So 2 to the power of 8 is 256. So if I add 4 to 253, we get 257. So mod 256, we get 1. Right? So using like a finite number of bits actually is already producing this modular arithmetic. So in fact, when you're working on your computer, you don't actually have arithmetic over the integers. You have arithmetic over the integers mod probably like 2 to the power of 63. It's not 2 to the power of 64 because we go from like negative to positive. So we just have to shift it by 2. Okay, what about this one? We're saying in an 8-bit system, if I do 16 and I multiply by 17, we're going to get 0. So this is just showing what happens, right? So 16 times 17 mod 256 is going to be 10, right? So just note that the integers as you're using them naked, right, are actually working in a residue class. Okay, so here is the residue class Z6. So again, we have numbers 0 through 5. So we can create that set by doing this. Right, so this is going to give us the set of numbers 0 through 5. I can ask for the type of that. It's going to be a range. And what I'm going to do here is just print out the multiplication table for this residue class. So the way that you read this is that those are one of your products and across the first row, and this is the other product. Or wait. So if you have A plus B, those are called summons. If I have A times B, what's A called? I forget, but when I say product und, but in any case, so this is one thing we're going to multiply by across the first row, and the other thing we're going to multiply by across the first column. So let me see. Those are, I didn't put those there. So we have to imagine 0, 1, 2, 3, 4, 5, 6, 7 across the top, and 0, 1, 2, 3, 4, 5 across the first column. So this is 0 times 0, mod 6. 1 times 1, mod 6. Yes, sir. That's addition. Oh, is this why I'm getting confused? Oh, this is addition. Thank you very much. Okay, so I think what I originally said was correct then. This is 0 times 0. 0 plus 0. 0 plus 1, 0 plus 2, 0 plus 3, 0 plus 4, 0 plus 5. Okay, so the same thing here. 0 plus 0, or 0 plus 0, 1 plus 0, 2 plus 0, 3 plus 0, 4 plus 0, 5 plus 0. So something like this is saying 4 plus 3 is 1 mod 6, which makes sense, right? 7 mod 6 is 1, right? So again, you can always write out one of these. I guess in this case, this would be an addition table. So just notice here, the addition table is symmetric, right? That is, it's equal to its transpose. And this can only happen if addition is commutative, right? A plus B has to equal B plus A. So the position at ij has to be equal to the position at ji. The additive identity is 0, right? Because you can see that this row is invariant and so is this first column. And each column and row has exactly 1 0, and thereby each element has an additive inverse. So what's the additive inverse for 4? Well, that seems to be 2, right? 4 plus 2 is 6, mod 0 is 0. So we can just walk through and then calculate the additive inverse for each element. So the additive inverse of 0 is 0, 1 is 5, 2 is 4, and so on. Okay, now let's do the multiplication table, which I thought we were just doing. This makes much more sense, right? Because the first row is showing what happens when you multiply stuff by 0 and reduce mod 6. That's the same thing happening along the first column. But what do I want to notice here? I want to notice that in every single column or row, there is exactly one instance. There may or may not be a unit. Right, so look at what this is saying. This is saying 1 times 1 is 1. This thing is saying that 6 times 6 is 1. 5 times 5 is 1 mod 6. But 0, 1, 2, 3, 4. 4 times nothing gives you 1. Right? There is no element by which I multiply 4 by to get 1 back. I can get 0, 4, and 2. That's it. So my question is, given that this is the multiplication table for Z6, are we able to call this a field? No. Why? Because there's an element that doesn't have an inverse, right? Actually, there's a bunch of elements that don't have inverses. Okay, so this is not going to be very good for our use. So just down here, I'm showing you which elements have inverses mod 6. So 1 has an inverse mod 6 itself, and 5 has an inverse mod 6 itself. Why does this make sense? What's another way of describing 5 mod 6? Minus 1. Right? It's just, you can sort of flip all the numbers around and go minus. Right? So 1 is inversed by 1, and minus 1 times minus 1 gives you positive 1. So it's not a surprise that for any residue class that we create, 1 is going to be invertible, and minus 1 is going to be invertible. Okay, Z6 isn't a field, right, because we found a bunch of elements that don't have inverses. However, ZP is a field when P is a prime number. And this is going to be critically important for us, okay? So now we're going to be, whenever we talk about a residue class, we're just going to presume that it's like has a prime number of elements. And when it has a prime number of elements, we're going to see that every element now has an inverse. So we're just going to play the same game. So I just replaced n equals 6 with n equals 5. That's going to give me 5 elements, 0 through 4. And let's look at the multiplication table. Now, obviously, we can't take the inverse of 0. That's the exception. I hope I did mention that, right? So a field is a ring where every non-zero element is invertible. Like, of course, we should never expect to invert 0. So we just have to confirm that every column here contains a 1. Okay, so there's a 1, there's a 1, there's a 1, there's a 1. And how do we interpret something like this? Well, this says that 3 times 2 is 1 mod 5. Is that true? 3 times 2 is 6. Mod 5 is 1. Okay, so this isn't proof, obviously, but it is an example that if we have a residue class with prime number of elements, that every non-zero element is going to be invertible. So here we go, just down here, I'm printing out what those invertible elements are. So 1 is inverted by 1. Oh, this is just saying elements with a multiplicative inverse, every one but 0. Okay, so we know that we're not going to be using the integers because that doesn't form a field. But if we restrict ourselves to using a sort of finite many integers, a prime amount of integers starting from 0 going to p minus 1, that is going to be a field. Right? So that's important. Okay, so the next thing we're going to want to do is talk about the greatest common divisor. You guys know what the GCD is? Surely it's like one of the most important things that they're going to teach you in number theory. So I'm just going to define it. So definition of the GCD, if I take two integers, not both 0, the GCD of anything in 0 is anything. So that's sort of a trivial case. We say that G, another integer, is the greatest common divisor of A and B, denoted GCD of A and B, when the following three properties hold, right? G is a number that both divides A and divides B. If H divides A and H divides B, H has to divide G, right? So that's sort of saying G is the biggest thing that can divide both A and B, because if anything else divides it, it has to also divide G. And the GCD, we're just going to distinguish that as being positive, because technically you could report either negative or positive cases in the GCD. So restricting ourselves to positive GCDs just gives us a standard way of reporting. So for example, GCD of 6 and 4 is the GCD of sort of the numbers inside. So 2 times 3 and 2 times 2, right? And you see that 2 is common to both. And so that's not overly interesting, but again, you have to keep it in the back of your mind that we're going to be redoing everything I just said using polynomials instead of integers, right? So I'm showing you the stuff about integers because it's not that different when we jump into another number system. It's just going to be a little bit more complicated. Okay, so just know that there's an inbuilt GCD operator in Julia. So we're just going to do a bunch of random tests here. So I'm just going to do this. So the GCD of those two numbers apparently is 10. So I can't really confirm that, but it is in there. Euclid's algorithm, or the Euclidean algorithm. So GCD is sort of like just partially the story. Actually, the GCD is just a special case of something called the extended Euclidean algorithm. And the extended Euclidean algorithm works over more than just rings. It actually works over something called a Euclidean domain. It's kind of like a circular type of a Euclidean domain is any domain for which you get the extended Euclidean algorithm. But all you need to know is that a polynomial ring is a Euclidean domain, and so are these residue classes that we're working with. So in both of the classes of objects that we're going to be working with, we're going to be able to have the Euclid's algorithm. So here are some properties of the Euclid's algorithm, which in fact define the algorithm itself. So the Euclid's algorithm is going to give you the GCD along with some other stuff called the Bézout's coefficient. So I'm first going to show you the non-extended version. So Euclid's algorithm, the one I'm showing you here, is just the regular old GCD. But the GCD algorithm more or less just falls out of these 3 points in this lemma, namely this one. Right? So the first one just says the GCD is commutative. Okay, that's not too big of a deal. This one's interesting. It says that the GCD of A and B is the same thing as the GCD of A minus B. Right? So this is already going to allow us to start reducing stuff. And here's another interesting thing. It says the GCD of A and B is equal to the GCD of RB, where R is the remainder of A mod B. So here you could put sort of A mod B. So in any case, those are two invariants on the GCD that are going to let us drive one of the inputs down. Like something is going to hit 0, because at each step we're going to be subtracting something. So if you want to implement this, it's very straightforward. There's Euclid's algorithm right there. Right? So we're just going to descend until something hits 0 and just keep on doing this remaindering, or each time. So that's pretty remarkable, actually. Okay, so if you want to use the inbuilt GCD, you have to sort of write this base in. But there you go. So I'm just showing you how we could write it. I'm sure the actual GCD operations in Julia are far more optimized than this naive approach. It's not even that great of an idea to do it recursively, because now we're paying for all these recursive stacks. But the recursive definitions are the ones that are the most nice for actually doing proofs, because you get a very clear rule about when you're allowed to replace stuff. Okay, so the extended Euclidean algorithm. Right? This is where things get more interesting. So the Euclid's algorithm we just looked at is actually just like a special case of this algorithm. And this algorithm is giving you 3 things: the GCD and S and T, which are called sort of Bézout's coefficients. So really, what we get when we give the extended GCD algorithm A and B are 3 things. Right? S, T, and G, which is the GCD of A and B, satisfying this property. The property being that AS plus BT is equal to GCD of A and B. Right? So this is sort of allowing us to express A and B as like a linear combination of one another, which is kind of cool. There's the algorithm. I'm just going to go in and print, and it's showing as an invariant this over like a bunch of inputs. So The first input was 4 and 12. Their GCD is 4. And indeed, 4 times 1 plus 12 times 0 was 4. Right? And these are all the numbers being reported back by that extended Euclidean algorithm. Let's do another one, maybe 9 and 12. So I think GCD here is 3. And 9 times -1 plus 12 times 1 is 3. Right? So this eGCD algorithm would have produced -1, 1, and 3. Let's do one more. 4 and 13, those happen to be coprime. And here it says 4 times -3 plus 13 times 1 is 1. So that's great. Just to mention that, like, the extended Euclidean algorithm is also implemented natively in the system, so you can use it. Here's the information on it. We just sort of did it so you could see it in the sheet. Okay, so why am I telling you this? Well, you have to think about what our objective is, right? I'm saying we want to basically create rules for doing arithmetic over these residue classes. And I'm saying these residue classes, when they're of prime characteristic, are fields. But I didn't say how we're going to be doing any of the inversion. Right? So if I say, what's the inverse of 3 mod 7? Of course, we can walk through the whole class and say, like, what's 3 times 1, 3 times 2, 3 times 3, and then, like, basically do a linear search for its inverse. But that's not going to cut it, right? We can't we're going to have to do an inverse a lot. So we're going to need a sort of better algorithm for finding inverses. And this is exactly what the extended Euclidean algorithm is going to give us. So I'm going to show you how that works. So notice the extended Euclidean algorithm computes inverses in Z mod n. So if you give me a non-zero element from Zn, then the eGcD returns S and T such that this is going to hold. If we take both of these sides mod m, what do we get? Well, this is multiplied by m, so it just becomes 0. So what are we left with? Well, we're left with a times s is congruent to the GCD of a mod n. Okay, but what does this mean? Well, this means that a times s is equal to whatever the GCD is. But if the GCD is 1 somehow, then we found the inverse of a. Right? So if the GCD is 1, we have found s such that a times s is congruent to 1. Which is what? The inverse. Okay, so this is very important, right? The fact that, so suppose this GCD here is 1. If I take this equation mod m, we have a times s is congruent to 1 mod m. Okay? How could we ensure that this GCD is always 1? Yeah, A and M, let me rephrase the question. How can we ensure A and M are always coprime? A is the thing that's moving. M we can set. Have M be prime. But remember what I said when we're working with these residue classes. I'm not even interested in the ones of non-prime characteristic. So for us, we're always going to be working in ZP. If we're working in ZP, that means the GCD of A and P is 1. Has to be, right? Because it's going to be coprime with the prime. So we're always going to be able to utilize this extended Euclidean algorithm to find inverses. So for instance, to find the inverse of 5, modulo 13, we do the following. So here's A and here's M. What I want to do is find their GCD and these Bezout coefficients, S and T. We sort of package that into a function called inverse mod. So what we really are interested in is S. I don't care about T. I don't care about the fact that the GCD is 1. So we can calculate the inverse of 5 to be 8. So let's ask ourselves if that's correct. So 5 times 8 is 40. 13 goes into 43 times with the remainder 1. Right. So we are able to find the inverse of 5, right, by doing this GCD computation. I wonder if I put that up here. No. Just wonder if I can just print out. Okay, let's see if this works. I extended Euclidean algorithm. I'm just gonna take this. I just want to call it 5 and 13. Hopefully this will work. Right. Okay, so there's the. That's not right. Oh, that's the. Right, this is the inverse. This is G, right, the GCD of those two things. And then we have the Bezout's coefficients. So why am I saying the inverse is 8 when this is reporting -5? Okay, so there's a weird behavior with modulo in Julia or in like other languages, in that it actually doesn't standardize if we're working in positives or negatives. Right, so remember when I said 5 is like -1 mod 6? -5 mod 13 is 8. It's like super easy to like calculate the positive version of a negative number because you just take like what you're modding by and subtract. Right, so -5 is 13 minus 5, which is 8. Right, so -5 is 8 mod 13. So just be very careful when you're seeing, you may think I'm expecting 8 but seeing a negative number. Just be careful. Right? Remember that we're working in an equivalence class where we really have to ask if these things are equivalent based on their remainders. So just be careful with that nuance. Chinese remaindering. Yes. Is there any way to force it to do that? Force it to do what? Oh, well, there's something called the symmetric mod and mod. But since you're the ones developing like all of the fundamental aspects of this system, it's going to be up to you. Right? So you can always write like a wrapper around the existing mod to like force it to go positive. Actually, what's best is to use the symmetric mod. When I say work mod 7, it's best to have the numbers -3 to 3. But it's again, it's up to you. Like the package that we've given you is like kind of a shitty package. Like that's sort of part of the project, is to like clean it up, give it better interfaces, and speed it up a bit. It's going to be a really informative project, working with someone else's code. Right? You'll start to understand the importance of comments and manuals, right, when you have to work on a very undocumented piece of code. Okay, Chinese remaindering. So this is something that's super important in computer algebra systems. Why? Well, as I said, we're obligated to work with the integers. But most computers aren't able to work with the integers, say, right? They're able to work like mod 2 to the power of 63, which is normally so big that, you don't notice that you're overflowing. For mathematical computation, yeah, our numbers are going to get explosively large. So we're going to need some type of provision for not working with enormous integers, but producing an answer with an enormous integer later. And that's precisely what this Chinese remaindering is going to do. So we've actually changed one of your tasks on your project. So I'm now making all of you aware of this. We were going to have you improve multiplication by doing interpolation instead, but then I'd have to introduce fast Fourier transform and a bunch of this other stuff. We're going to have you do Chinese remaindering instead. It's going to be a little bit easier, but still very satisfying. So here's the basic form of the Chinese remaindering theorem. So suppose you give me two integers, a and b, and they're relatively prime. You can give me a finite sequence of relatively prime integers, m1 through mk, called the moduli, and the corresponding integers u1 through uk, which are their images, right, so that you form some type of system like this. So again, I'm trying to recover u, and you've given me like u1 mod m1, u2 mod m2. So basically you're saying, U is known to me, but I'm only going to tell you what it looks like in these sort of equivalence classes. And can you then reconstruct it? And the answer is yes, I can. Right? So here's an example. If I know that U is congruent to 4 mod 5 and U is congruent to 5 mod 7, we want to deduce the fact that U is equal to 19, right? Because 19 is congruent to 4 mod 5 and 5 mod 7. Right? So the idea here is that you're going to write a multiplication algorithm that instead of using an arbitrarily large integer is going to restrict itself to like Z5, right? 5 integers. So that's surely going to be faster than working with arbitrarily large integers. And then you're going to do the multiplication algorithm for a bunch of other stuff, right? You may say, what's the product mod 5? What's the product mod 7? What's the product mod 11? What's the product mod 17? And tomorrow I'll show you how many primes that you need to use in order to be ensured that when you use Chinese remainder theorem, you've actually reconstructed, right, the whole thing. Right, so that's the intent of this. Right? We're going to use Chinese remainder theorem to lift stuff from small residue classes to the entire integers. And that's a hell of a lot faster. Because you can imagine if you take any number that's enormous and like find its image mod 5. That's like has to be tiny. It has to be a number no greater than 4. And And moreover, when we take modulos and we're making sure we're modding out by primes, like we get extra properties like, oh, okay, now we can assume we're working in a field. Like we assume that division is going to be something that we can use, no problem. Okay, so that was the example of Chinese remaindering. This is the theorem behind Chinese remaindering. So normally we say that the requirement for M1 and M2 is to be coprime, but we're just going to let all the M's be primes, right? So then they're going to be coprime sort of naturally. So if you give me M, right, the product of a bunch of primes, there exists a unique U mod M such that U is congruent to UI mod Mi for I 1 through K. Okay? The proof of this isn't actually that bad. At least the proof of its existence isn't that bad. This is a constructive proof, right? This is the world that I live in, right? Rather than just showing, if it didn't exist, some weird property triggers. Like I'm actually going in and saying it exists because here's the construction to create it. So here's U. Suppose it's written like this, right? V1 plus V2 M1 plus V3 M1 M2 and so on. So each of these things here, I'm just sort of removing, I'm just adding like one more of the M's, right? So if this was like none of them, one of them, two of them, the next one would have three of them, this one has like all of them. Okay, so notice if I take this U and I reduce it mod MK, like if I reduce it mod M3, I'm only gonna have like these terms. If I reduce it mod M2, I'm only gonna have like these terms. So the idea is that you take this equation, you reduce it mod M1, right? So what do we have if we reduce mod M1? All that's left is this, right? U is equal to V1. So here we can conclude that U1 is congruent to V1 mod M1, right? And U1 is explicitly given to us as one of the inputs. Okay, now that we have U1, we can sort of back substitute and do the same thing again, right? And we can find here that U2 is congruent to V1 plus V2 M1 mod M2, right? That's just sort of doing a solve, right? And I'm just showing you here what you actually have to set V2 to, right? So then at that second step, you can calculate V2, right? And you just keep going, right? You just keep increasing the mod, right? And putting the stuff in that you know. So it's best for you to go through this construction like with a real example, right, to see how it works. Because again, right, when I learned CRT, like we spent an hour on it, and I'm just sort of saying, here it is, right? Learn it, use it, and deploy it, right? But we told you guys this was going to be challenging. But this is a very nice proof, right? It all comes down to writing U like this. I left out the proof of uniqueness. You can give it a try if you want. So here's a little bit of a trace, or like a real example that you can use, because you're going to have to implement the Chinese remainder theorem. So here's a bunch of UIs, right? So 2, 1, and 1. And here's a bunch of M's, 5, 7, and 3. So remember, the goal is we're trying to search for a number U that's 2 mod 5, 1 mod 7, and 1 mod 3. And what I'm just doing here is just walking through exactly the steps that I showed you in that construction. V1 gets the first one, first UI. V2 gets this. But notice here we're already obligated to start using our inverses, right? But thankfully M1 and M2 are what? Coprime, right? For two reasons, right? Chinese remainder theorem obligates them to be coprime, and we're always going to choose primes for M anyways, right? So we are guaranteed to get our inverses here. But when we say inverse mod, you think extended Euclidean algorithm, right? Not some division algorithm, right? That's what we get to, like another way of seeing this is like you're dividing. Right? You have to think about division being equivalent to multiplying by an inverse. Right, so I'm just going to run this. Inverse mod not defined, probably because I didn't hit this. Great. We have a solution. Okay, so this goes through and it says, oh, the number you're looking for is 22. So let's just ask ourselves if this is correct. So 22 mod 5 is what? So 5 goes into 22 4 times with a remainder 2, right? We can get 20. What about the second one? 22 mod 7. Well, 7 becomes 21, so we're left with 1 over, so that's a 1. What about 22 mod 3? Well, that's also 1, right? Because we get to 21. Yes, sir?
So you said it's unique, right?
It's unique, yeah.
What if you square it?
Square what?
The number you get.
Uh,
It would satisfy all the properties.
will it?
One times one. Wait, no, never mind. No, wait.
I don't think it's going to, I
Never mind.
don't think you can just square the number. And yeah.
But I think there is, it is, because we did it in another course, and we have to like find the lowest.
Oh, okay. So maybe did I put a...
Can you divide by the greatest common?
Well, no, I'm saying it's unique in this residue class.
Right.
So,
Oh,
right? So you don't get to like, yeah, I see what you're saying, but you're working over the whole integers. Whereas I'm saying like you get these numbers, right? So, because you have to start off with this m. So right out of the gate, we're restricting ourselves to like a finite slice of the integers. But if I didn't, what you said would be true. But yeah, thanks. More questions. Like we have lots of time. Like I know I'm burning through some of this stuff, mostly because I don't know what stuff is just review and what stuff that I really have to like dive down in. So please do interrupt me. I may have to take a break soon actually just to get some water, but we'll see. How are we going? Okay, so let's see if this is a good stopping point. Okay, I'm gonna maybe do... Actually, you know what? You guys want to take a 10-minute break? I think we're at that time anyways. 10 minutes? Okay. Does anyone know where there's like a water station around here? Like outside this building? Outside the door? Okay. So 10 minutes. Come back.
Yeah, yeah, listen. You can add zeros many times as you want. And as you say, you can multiply by an arbitrary amount of ones.
Oh, no, if you have a zero, that won't change the number.
Let's see it then. If we're like allowing to escape through the residue.
Yeah, no, but
So I'm saying this, if you have a 0 through 6, you're working lots of it. And I'm saying the number's 3 lots of it. The number of 4 is not 10. I'm trying to understand what you're saying.
oh, no. So you add, no, to get the next one, you add. Yeah, I'm trying to like add.
Yeah, you add the product of, you add what you want to multiply. So
Yeah,
if I said it was like 7 mod 15, like 3 times 5, I can add 15. As many times as someone doing. That's 0. It's like adding 12 hours to any single class.
Yeah. But no, but if you're doing Chinese, you have to do it for all 3 classes that you're doing. If you're doing Chinese, like all of the classes that you need. So it's more.
Wait, write it down so there's a real example.
Yeah, no.
And then I appreciate
I just realized if you. Yeah, that's what I was like. Yeah, that one. Yeah, so. Yeah, so if we have.
So I have my image, I have you, and I have all of the images. Suppose we found you. Right? So what do I do now?
So no, so if it's 5, if your classes are 5, 7, and 11, you add 5 times 7 times 11.
Right, but that's a 0 one.
Yeah. That's 0, so 0 mod 5, 0 mod 11, and 0 mod 10. So.
But then your minimum doesn't make sense because I can also subtract.
Oh, yeah, well, minimum positive.
Oh, okay. So minimum positive into positive.
Yeah, minimum positive. Yeah, so to get the minimum positive, so after you do the Chinese remainder theorem, you divide by the.
We do a remainder.
At least come multiple, I think.
Why does it?
Yeah.
Why does it tell?
Wait, it's in my assignment. It's in my assignment.
But I don't think there's anything with a square.
Yeah, no,
That's
it's
where
squaring it. No,
it doesn't make sense.
Yeah.
Okay, so how's it going? Like, how much of this stuff has landed before we start talking again? One thing? You guys, ask me more questions. 'Cause again, like I haven't been teaching in Australia very long, so I don't know what type of information to take for granted or not. But that was sort of just like crash course in number theory. The rest of this stuff is going to be the factoring. So if you don't really need to understand anything I just talked about, except for Chinese remainder theorem, but that shouldn't be too hard. Julia probably even has CRT built in. I'd be surprised if it didn't have CRT. I'll just wait a few more minutes for everyone to get back. How are you doing, chat? Any questions? Oh, you have it?
Now I'm interested that you told me you could generate arbitrary more images that have the same property. But I think you can only do that by like adding 9 times 11 times 13.
Yeah.
Because that's 0. So that's not really that.
Yeah. But you can.
But I'm not sure the algorithm will ever produce the non-smallest thing.
No, it does.
Okay, so show me.
No, so you do it, you get this, and then because it's greater than.
Oh, okay. But like, so when I'm doing in my examples, my operations always happen within the.
Yeah, no, I wasn't realizing that it was all in a particular
opportunity to even do larger than the product of those.
Yeah.
But that is a good point, right? If you're just working this out by hand, using regular arithmetic, you may generate something that's much larger. But yeah, all that you require there is to do one remainder
Yeah, the remainder of the product.
of whatever you get, yeah, minus the product. And it will give you the image inside the product.
Yeah, so this one, this course, is the only one, only second year course does the focus on three stuff. So,
Have most of you guys taken it? Have most of you taken the number theory class?
2301.
Okay, well, so I'll see you around the following 2 Wednesdays, right, in this health session. So be sure to come. Again, stop me if I've said something that doesn't make sense. I'm going a little bit fast. So, but we can all just sort of, just understand that we're doing a different type of arithmetic. Like we're working on a clock. We're never using all those integers. And what comes as a consequence of that. The Chinese remainder theorem is quite fun. Go through that group, you'll see. It's quite simple. Okay. Does anyone notice if anyone's missing? If you're not here, raise your hand.
Okay, chat, you ready to go again? Apart from the CRT stuff, what would you say is the most important? Apart from the CRT stuff, what would you say is the most important thus far? The fact that we can take inverses in the residue class of prime characteristic, right? The fact that when we're working ZP, every number has an inverse. That is to say that we are working in a field. Right? The fact that we're guaranteed to be able to divide all of our numbers is super important, right? Because this wouldn't work in Z8. Right? It works in Z6, works in Z7. So yeah, before we start doing like the second half, which is like the computer algebra part, like fire off your questions. Don't be ashamed. I asked lots of stupid questions when I was in school. Okay, so if really nothing needs to be clarified, that's okay. You can read through the notes and we can talk again on Wednesday. But please do stop me now, right? I'm sure none of you have seen, I guess I can't be sure. I'd be very surprised if any of you have seen the stuff that I am now going to present. Yes, sir. 2301.
Yeah, the course I did trying to remind it does polynomial related in.
Yes, right, so yes, but like now this new stuff you won't. I doubt this would be in your number theory class. So really, you need Galois theory. Has anyone here taken the Galois theory course yet? No? In your number theory class, did they teach you about Fermat's Little theorem?
No, so it's abstract algebra, number theory, and linear algebra.
Oh, wow, that's a tough course. Yeah. That's a lot of stuff to teach in one course.
It's a horrible course. Don't take it.
Okay, I won't take it, but given I have a PhD, I don't think I need to take more courses. I'm done with that. Oh, really? Yeah. I take it back. Some of you may have. Okay, well then, good. Right, but for those of you who haven't taken that 2301, find someone in this course who has and buddy up. It'll be beneficial to both of you, right? It's peer learning actually is one of the most effective ways of educating yourself, right? By trying to explain something to someone else and having something explained to you by someone else. So the fact you've enrolled in university, it's like one of the point of being here is working together. I don't know what Yanni's stance is on working together, but my perspective is as long as you're not sharing code with one another, everything else is fine. Like you should be sitting in the pub arguing with one another over proofs and stuff like this, giving each other examples, yelling at me. I don't know. Okay, so let's go on. But again, promise to stop me, chat, or humans here. If I say something that's wrong. I may start saying things wrong on purpose just to see if you're paying attention. Okay, so now we need to repeat everything that we've done with integers with the ring of polynomials. Okay, and this is going to be easier if we just let go of the fact that we were using integers. A mathematician doesn't really care about the object we're working with, right? I just care that we're working with some objects, product is defined, they're invertible, Like the numbers themselves I'm not interested in, right? It's the algorithms and the operations definition which is the thing that is interesting. So if I say that the polynomial ring is a ring, right, immediately you should think, oh, okay, that means I get addition, that's commutative, I have zeros, I have additive inverses, but I probably don't have, or I don't necessarily have division. Right? That's when I say something's a ring, like those are the lights that should be going up. So by this point in your mathematics career, you have surely worked with polynomials. Right? That much I'm sure of. So a polynomial is something like x squared plus 2x plus 1, but not like x squared plus 1 over x minus 1 or x sine x. So x squared plus 1 over x minus 1 is what we call a rational polynomial, and that really changes the game. X sine x isn't a polynomial because it contains sine x. Do you know what category does sine x fall into? Special functions. Right, so we have all of these notions of special functions. That's anything that you'd have to integrate by looking up in a table, essentially. I'm not saying that sine isn't periodic, but there's a larger class of function called special functions, for which sine is one of them. Okay, so if you let R be a ring, and I say A is in Rx, what I mean to say is that A is a polynomial whose coefficients are taken from R, and whose free variable is this, x. Okay, so a polynomial in its general form looks like this, right? So we say it's an times x to the n plus an minus 1 to x to the power of n minus 1, where some of these coefficients may be 0, but not the leading one. Right? I don't want to say something like 0x cubed. That doesn't make any sense. Okay, so we're just, in order to standardize the way we write polynomials, we're going to enforce the fact that the leading coefficient has to be non-zero. Okay, other parlance. The degree of A is n. That's this, so the degree of this is 2. The leading coefficient of A is an, so that's the leading coefficient. This one has leading coefficient 1. 1, right? Just because it's not written doesn't mean it's not there. And have you guys fixed your pretty printers yet? Right? To not print units. Great. And then the leading term is going to be this, an x to the power of n. So a polynomial is something that is comprised of terms. It's like a finite sum of terms. And if you look in your project, we've defined a type term, which polynomial sort of like derives from. So polynomial in your project is going to be, I think at this point, a heap of terms. A heap's not the best way of representing it, so we're asking you to like remove it and put something else in. There's just a couple conventions. We say that the leading coefficient of 0 is 0. The leading term of 0 is 0, which is not too surprising, but this may be surprising. The degree of the 0 polynomial we're going to designate as minus infinity. This just simplifies a lot of the theory, right? Because often we want to distinguish 0 from like a non-zero polynomial like 1, right? So 1 is a polynomial, but its degree is 0. 0 is a polynomial, but I don't want to call its degree 0 because it's sort of less than a constant polynomial. It's the 0 of the ring. So it does merit some sort of special, I don't know, distinction in its degree. So just keep this in mind. Okay, so how now do I prove that this polynomial ring is a ring? Well, all I need to do is demonstrate that it has an addition operator and a multiplication operator that satisfies the axioms for being a ring, right? Commutativity, additive, inverse, right? Multiplicative identity. So I'm saying here is addition. And like, what is this addition output? Addition. I'm not sure many of you have ever seen sort of something strange like this, but I'm saying, no, like this is what I'm defining the addition operator for polynomials, right? As this algorithm, which is sort of mathematically sound, so we can just look at it. So you can just imagine what happens. So one thing you have to, so like, what is the hard part of adding two polynomials together, right? If I have two polynomials, what I want to constantly keep doing is looking at their leading term and then taking the bigger one by degree. Or if the two polynomials have equivalent degree leading terms, I want to sort of merge, right? So 3x squared plus 2x squared should be 5x squared, right? Because the degrees match. but 3x squared plus 5x is 3x squared plus 5x. There's no merging required. Right? So this addition algorithm just essentially implements what I've stated. Right? If the degrees are the same, right? So I'm going to give me two polynomials. If the degree of the polynomials are the same, that means their leading terms have equivalent degree, which means that I have to merge them, right? When I'm adding them. So what's special here? Well, like I'm saying, here's another plus, and you'd be right to complain about, aren't you defining plus with plus? A little bit, but I'm defining addition over polynomials, and I'm reducing that to addition over terms. And I can define what it means to add two terms together, right? So if I want to add two terms like this, ax to the n plus bx to the n, that's just a plus bx to the n. Right? So really what I need to do is just define a few properties on terms, which will then propagate out to addition. Right? So this is the hardest part of the addition, right? If I need to merge the term, merge them, and then just recurse, right? Remove the leading terms and continue. If degree of A is bigger than degree of B, right, then just strip A of its leading term and recurse, right? I'm just sort of removing it. If the degree of B is bigger than the degree of A, oh, that should be a B. And then add, right, then recurse. Okay, so that's the pseudocode for it. This is the implementation in your project for it, which is a little bit different because it's been implemented with heaps, right? But you can study sort of like how that relates to one another. But it's essentially the same thing, right? If the degrees are the same, right, push into the heap, and where this addition is addition on terms. So when you're looking in your project, right, all arithmetic on polynomials is going to boil down to arithmetic on terms. And just to show you how this works, so what this does is just create the x polynomial. It creates the polynomial x. And because we've overloaded all of these addition and power operations, it gives us an easy way of defining polynomials in a more natural way. So here I have P1 and P2. So this is 2x squared plus 3x minus 5, and minus 3x squared minus 4x plus 6, right? So like this is going to require a merge at like every recursive level. So let's just ask what the first thing should be. It says 2x squared minus 3x squared should give you minus 1x squared. 3x minus 4x is minus x to the power of 1, and minus 5 plus 6 is 1. Okay? So your pretty printer shouldn't be doing stuff like this. This is dirty. Right, so, but please do check that your pretty printer in this case will give, this is a good test case for your pretty printer, right? Because this should be minus x squared minus x plus 1. And so you might want to jot this down and use it as a test case. Okay, so that's addition. That wasn't too bad. Okay, so multiplication. This is something maybe you should pay attention to more closely because this is like explicitly part of your project, is to create a new multiplication algorithm that is faster. Okay, so first, this multiplication algorithm that I work here is different than what we've implemented in the system. This is like the most naive way of implementing multiplication. This is a better way of implementing multiplication that sort of does divide and conquering. And I actually think that it's more clear, right? More clearly stating how it works than the naive algorithm. So check this out. So we want to multiply two objects that are polynomials. How do we do that? Well, if either of them are 0, the product is 0. Okay, that's a base case. If the leading term of A is A and the leading term of B is B, what does this mean? I mean to say that the polynomial is just a single term. So if the polynomial is a single term, then returning their product is doing a product of terms, not a product of polynomials. Right? So again, I've reduced taking products of polynomials to taking products of terms. So how do I multiply two terms? Well, AXN times BXM is AB, that's the new coefficient, and x to the power of n plus m is the new sort of unknown, the new variable. Right? You guys all know this. X squared times x cubed is x to the 5th. Right? So I'm just sort of making it very explicit what's happening here. So again, the base case for this multiplication, this divide and conquer, is to say, if you're a polynomial of exactly one term, I can multiply you against another polynomial of exactly one term. Okay, so if we get to here, we're assured that the polynomial is not 0. We're assured that the polynomial has more than one term. So I'm saying, okay, if you get here, break up your polynomial into two pieces. I don't really care how you do it, as long as you're not doing something cheeky, like saying, oh, I am 3, how can I say this? Like, I don't want you to just keep adding a bunch of like zeros at the end, right? So like, you can't say I'm 3 plus 3 minus 3. That's not a fair rewriting. You can take x plus 7 and separate that into x and 7, but you can't separate that into like x plus 7, x plus 8 and minus 1. Right, so that's what this thing here will ensure. Right? So I want you to take A, I want you to break it apart into two pieces, and the two pieces can't have equal degree. Right? That's going to force one of them to have smaller degrees. So again, right, they're not zero, they're not single terms, so just take your two polynomials, break them up in whatever way you want, and then just utilize the distribution property. Right, so how does distribution work? Well, it says A1 plus A2 times B1 plus B2 is equal to this. Right? Like all of the products distributed. But what's true about the thing on the right? Well, A1 and B1 and B2 and A2 are all necessarily smaller than A and B. Right? So this step here has taken the product and converted it to a sum of smaller products. Right? And eventually those smaller products are going to hit this base case down here, or this. Right, so this is a good framework for implementing the multiplication that we're telling you to implement. Right, for instance, if you store your terms in a list, it's really easy here just to cut that list in half, right, and to pass it along. The other thing that you're going to need to do is create a multiplication routine that works mod p. Right? I haven't done any reductions in here. Right? You're going to have to do this for the polynomial mod p type that you're introducing into the system. And so you want to do this, but like with the additional, like you want to do this essentially. I want you to write this multiplication routine to work in ZP. So this is you can do it exactly like this, right? It's so clean that it's going to be pretty tough to make mistakes at this level. Right? And you can always try playing around with this one. So this one's different. It still works like this, but it just does one term at a time. It's sort of saying, oh, so how could I take f times g? Well, that's leading term of f times all of g, right, plus the rest of f times all of g. So it's like it's the most naive way of doing it. Oh, that should be a product. I just want to show you that like we can indeed do multiplication. Where is p not defined? Here. Okay, so like there's P1, there's P2. Let's just check. So a quick way of checking that your arithmetic works is to simply check the last term and the first term, because those two things are like totally predictable. So the leading term of the product has to be like the product of the leading terms. So this was 2x squared, that's minus 3x squared. So the product of those two things are minus 6x4. Okay, great, that's there. What's the constant term here? Or what's the term of least degree? That's going to be minus 5 times 6, so there's my 30. Right, so that's a good, right? If that wasn't the case, you'd know you're wrong, but only knowing this is not enough. But it's good just sort of as a first sanity check. Okay, so as I mentioned, like this multiplication that we just defined, like is a proper it's a proper product for this ring, but because the ring is an integral domain, it's also going to satisfy the following properties, right? Mainly because it has to define the following properties, but sometimes they're useful in proofs, right? So the degree of a product of two polynomials a and b is equal to the sum of the degrees. The leading coefficient of a times b is equal to the leading coefficient of a times the leading coefficient of b, right? Same thing for the leading monomial, same thing for the leading term. The leading monomial is just, so like 2x squared is a term, 2 is the coefficient, x squared is the monomial. My whole master's degree was basically talking about monomials and how to order them. My whole master's degree was on polynomial arithmetic. Right? It's so fundamental in the computer algebra systems that any gains we make at the arithmetic level make everything else that use arithmetic faster. Right? So, and basically everything will use the arithmetic. So there's a lot of like putting a lot of effort in at like the very foundation of your system is worth it, right? Because it can have such staggering positive benefits. And the same is true the opposite, right? If you make a fundamental change at your foundation that's bad, that can have a negative effect, right? I remember when I was working at Maple, they made the decision for sets to return ordered, and like we almost had a revolution at the company, right? Because like every single package took an efficiency hit, right, from the fact that they were ordering those sets, which didn't make any sense, right? Sets aren't ordered. Why should we return them ordered? But, you know, sometimes that's what marketing wants. Here's just a proposition which you can try proving if you want. Every field is an integral domain. So the only reason I want this is so I can say, oh, when we're working with ZP, that's a field which is an integral domain, which means we got all these sort of nice features. Okay, so we've learned how to add polynomials together. We've learned how to multiply polynomials together. Let's pause and think about something. If we have like the polynomials, just like generic ones with integer coefficients, will the sum of two polynomials always be a polynomial? Yes. Will the product of two polynomials also always be a polynomial? Yes. Right? Like if I take a polynomial, well, again, here, right? This proves it. Right? This is going to return a polynomial, so the product of two polynomials has to be a polynomial, right? Proof multiplication algorithm. Is it necessarily the case that the the ratio of two polynomials is a polynomial? Yeah, definitely not. Right? So this is where the fact that we need to work in fields becomes critical. So consider this one, right? We are unable to divide in Rx. What is x squared divided by 2x? Well, that should be 1/2 x. So we're going to need some way to rectify this. So we could say that if we move to polynomials with rational coefficients, then this would be fine. But I don't want to use rationals, is what I've said. So, okay, we're going to make this is the compromise. We're not going to use rationals. We are going to use a field, but we're going to use the field ZP, like a residue class. So I can do this exact same division here over mod 7. So now we have x squared divided by 2x. Mod 7 is what? Well, that's going to be equal to 1/2 x mod 7. But now, how do you have to read this? You don't read this as 1/2. You have to read this as 1 times the inverse of 2 mod 7. Right? So I may write fractions like this, but like interpret them as inversions. I'm just keeping them as fractions because it looks a little bit more friendly. But again, 1 divided by 2 is the same thing as the inverse of 2. And how do I find the inverse of 2 mod 7? The extended Euclidean algorithm. You just take the extended GCD with 2 and 7, right? And that's going to report back 4, because 2 times 4 is 8, mod 7 is 1, thereby the inverse of 2 mod 7 is 4. So if I make the coefficient field, if I make the coefficients a field, then we're always going to be able to resolve coefficients not dividing equally. What we're never going to be able to resolve is like polynomials not dividing equally. Right? There is no coefficient field that I can work in where x over x squared becomes possible. Right? So we also have to restrict polynomial division to only be a division where like your numerator is sort of obligated to be higher degree than the one underneath. It sort of won't matter because we're not going to define division per se. We're going to define quotient and remainder. Right? The same way we define there is no division on integers. Right? That's why we needed to introduce quotient and modulus. Okay, so here's the division theorem that we've seen for integers, but I'm just going to like restate it for polynomials. Okay? So if you have two polynomials, and now this f is sort of indicating that the coefficients have to be a field. So whenever you see this f, you can just think ZP if you'd like. So if we have two polynomials and the denominator isn't 0, there exists unique polynomials q and r from that polynomial ring such that a is equal to bq plus r and the degree of r is less than the degree of b. This is sort of pointless because if r is 0, then this has to be true. So we can actually go ahead and prove the uniqueness. This one's actually not too bad. So I'm saying if you run there is a division algorithm over polynomials with coefficients from a field such that the quotient and remainder are going to be unique if they satisfy these properties. So let's prove that that's the case. So towards a contradiction, right, assume that I can write A as BQ1 plus R1, and I can write it as BQ2 plus R2, right? And they all satisfy these. So let's ask ourselves what is consequent from this. Well, if this equivalence is correct, then I can just sort of do a regrouping, right? So I'm going to put all the stuff that are multiples of B on the left and all the rest of the stuff on the right. Right, so this implies that B times the difference of Q1 and Q2 is equal to R2 minus R1. Okay, this implies that B has to divide R2 minus R1. Do you see why? Like the left-hand side is a product of two things. Therefore, the right-hand side is kind of also a product. So B is, it's ensured that B is going to divide the left-hand side. So B also has to divide the right-hand side. So what can we deduce by knowing B divides this difference? Well, the degree of R1 and R2 are less than the degree of B, right? That's one of the requirements. That's something that we've assumed. But the only way that this is possible then is for R2 minus R1 to be 0, right? That's the only polynomial with strictly less degree than B for which B can divide. Okay, but if these two are equal to 0, then they're just properly equal. Okay, well, let's hope that the quotients then are different. Okay, so, but now I return to this line, and I know that B times the difference of Q's is equal to 0. Okay, but we know that we're working in an integral domain. And in an integral domain, you can't have zero divisors. That's one of the properties of an integral domain. Do you guys know what a zero divisor is? Be honest. Okay, so in residue classes that aren't prime characteristic, bad stuff can happen. So suppose we're working mod 8. Is 2 non-zero? Is 4 non-zero? Is their product non-zero? Isn't that weird? Right? So some rings, you can have non-zero elements which you multiply to get a 0 element. Right? That sort of screws up a bunch of stuff. So we don't want that. Right? So rings which don't have 0 divisors are called integral domains. And all fields, in fact, are integral domains. So the fact here that B times Q1 minus Q2 can't be 0, right? Otherwise, B would be a 0 divisor. So since this can't be 0, right, one of those two things have to be 0. Well, we assumed B isn't 0. So therefore, this is 0. Well, if this is 0, then they're the same. Okay, so what did I do? I assumed that I could write A twice, like in two different ways, and then deduce that actually these two different ways are equivalent. Therefore, uniqueness. Existence is a little bit more tricky, but you can give it a go. Here's the division algorithm. You just have to, surely you guys have learned how to take, you've taken calculus, right? And surely you've learned partial fraction expansion. And in partial fraction expansion, you are obligated to learn how to do polynomial divisions, right? Like the first step of partial fractions is like if you have like f over g and f has degree bigger than g, you have to do a division before you can undertake partial fraction expansion. Is this all? Did you guys do calculus? Did they teach you partial fraction expansion? Maybe you just all forgot it once you walked out of the exam. Ah. Okay, so you guys got handheld a little bit. Okay, so no worries. Okay, so this is perfect. Thank you for speaking up, because this is definitely something that I would have presumed you knew because of that. In any case, it's a good thing that I then have a very nice worked example here. So let's just go through this knowing that there's a worked example. Okay, so we're going to do polynomial division, like long division, and it works almost exactly the same way that you do long division on integers. What you're trying to do is just reduce the degree of your remainder each time. So how does this work? Geez, how does this work? So this is better. Can I get a dock camera? Yeah, this is a very limited version of LaTeX. I couldn't actually do the long division. But okay, so let's look at the algorithm, and then maybe we'll walk through the worked example. So this is how division works. You give me two inputs. So now we are working in a coefficient ring, which is a field. It's ZP. This is quite important, right? Because now you have to regard all of these intermediate arithmetic as also happening within this field. So you have to be very careful that everything in the input is actually defining like what the arithmetic is doing inside, right? Because you're presumed to be working in a particular ring or field. So we start off with a remainder and quotient, and you set the remainder equal to the numerator and your quotient equal to 0. And what you keep doing is you're trying to keep reducing this r by trying to remove q's from it. So this is going to ensure that your division of terms is going to be clean, right? It's really more appropriate if we had long division. Maybe tomorrow I'll bring one. But again, we've reduced division of polynomials. We've reduced that to doing a division of terms. And I can sort of explicitly say how to divide two terms. So a to the xn divided by b to the xm is going to be, right, x to the n minus m and a over b mod p, by which I mean a times b inverse. Right? So you're not going to generate a fraction, right? But you're still sort of dividing two integers. You're just doing it in this field. So this may be a little bit weird, but just sort of go back up to this example, right, where I said, where did I put it? Here, right? That like we're doing this, but like there are no fractions in these residue classes, so that's how they become that. Okay, so let's try to go through this division. So I'm trying to divide a, which is 10x squared plus 4x plus 1, by 5x minus 3. And I'm doing this in Z11. So r gets 10x squared plus 4x plus 1. Q gets 0. So this is just checking the while loop. So you can go ahead and trace this yourself, but this is the while loop. So r isn't equal to 0. The degree of r is 2, which is bigger than the degree of b, which is 1. So I'm saying t is going to get this term. So 10x squared divided by 5x, that gives us 2x mod 11. Q is going to be incremented by 2x. And then this is the important step. I'm going to redefine r. But in the division algorithm, this r is obligated to monotonically decrease in degree. So in fact, this too was chosen very carefully, right? So that's what this t is calculating. This t is calculating a polynomial, a term, for which this product is assured to eliminate the leading term here. Right? So 2x, 5x, that's minus 10x squared. Boom, that will get rid of that. Right? So now the new r has degree at least 1 less than it did before. So it passes the while loop. I'm going to find another t. This actually is called the syzygy. Q is incremented, and again, I need to eliminate this 10x, and I'm being told just multiply q by 2, and that's going to do it, right? So this is minus 10x, so that will get rid of this. R becomes 1, and now that triggers the while loop condition off, and we return 2x, 2, and 7, right, which were the values there. And notice here 10x squared plus 4x plus 1 is congruent to 5x minus 3 times 2x plus 2 plus 7 mod 11, right? So this is a is equal to, which one was q? Yeah, a is equal to b q plus r mod 11, right? This invariant is only going to hold in the residue class. If you took that mod 11 off, it's not going to work. So be very careful in your project, right? That you're actually, if you're comparing something, so it's best not to look if two things are equal. It's best to take their difference and ask if it's 0, right? Because you can always say, like, do the reduction. Because a bunch of stuff may happen if you say, is f mod p equal to h mod p? Like, the coefficients may be off, right, in terms of the plus minus, but their difference is assured, right? Two polynomials are only equal if their difference is 0, right, in any ring. Okay, we also have, how much time do we got left? Okay, that's pretty good. We also have GCDs in this polynomial ring. I'm not really going to go through this, but it's almost identical to the extended GCD algorithm of integers, because this ZPX is an integral domain, right? So anything with an integral domain is going to get you this extended Euclidean algorithm. That may not be true, but it's certainly a Euclidean domain. I forget how they're stacked, right? So This ZPX is at least a Euclidean domain, which ensures that we're going to get the Euclidean algorithm. This is how it's implemented in the system in Julia. And then I'm just going to show you that it works. So I think it's going to do the same thing. Oh, no, sorry. This is we faked this one. Somehow we had trouble bringing it into the Julia sheet. But this gives you the same stuff, right? It's going to return the GCD of the two polynomials and these Bézier coefficients, S and T. Now, we're not going to talk about this, but I can show you how to keep, instead of modding out by a number, I can show you how to mod out by polynomials themselves. They create something called an ideal. And this extended Euclidean algorithm for polynomials is actually showing you how to take inversions in those ideals. Right? So I can keep, because you have to think that everything I'm showing you here has to be extensible. I want to keep adding extra variables now. I want to say, let's do it all over again, but I want to work over zx, y, right? Because eventually you want to get multivariate polynomials. We're not going to do that. That's where things got fairly hectic. But you want to play around with this GCD operation here. Okay, Unit 5, factorization, right? The whole sort of purpose of everything I just showed you was to come to this point. So I'm now going to show you how to factor polynomials, and the manner in which we factor them is actually very clever. It's not the most fast algorithm, but it's also not the worst algorithm. It's something very serviceable. So let's first go ahead and define a bunch of stuff in order to define the factorization problem. So when you have an integer and you factor it, the integer factorization is into primes. Right? You need some type of fundamental building block of integers. I think this is like the fundamental theorem of algebra, actually, right? That any number has a unique decomposition into primes. Fundamental, what did I say? Okay, it's the fundamental principle of arithmetic or something. Right? When you take number theory, they're going to say that like day one. Right? The most important thing in this class is the fact that all numbers have unique decomposition into prime numbers. We want to do something analogous to this. So what is the analogy to primes? Well, there's something called irreducible polynomials. To be irreducible means that you don't have a factorization. This gets kind of tricky, though, because the factorization depends on the numbers available to you. So let's take a look down here. So consider x to the power of 4 minus 4. Well, this is going to have different factorizations depending what set of numbers you're allowed to use as your roots. If they're saying, look, you're limited to z, right? You're working over zx, then I say, okay, I can factor f like this, right, into the product of two polynomials from zx. If you say, well, actually, go ahead, you can use all of r, then I say, oh, okay, so you're giving me algebraic numbers, so I can go a little bit further, right? I can actually take this one and split it into plus minus the square root of 2. If you say I have complex numbers, actually, I'm guaranteed to be able to decompose this polynomial into a product of linear factors, always. And this is why these complex numbers are sometimes called the splitting field, because the field splits any polynomial that you can define in it, which is interesting. But it's sort of tough. We can't really work here. We're sort of limited to working in here. But it is important to understand that the fundamental building block of a polynomial depends on what coefficient ring you're allowed to use. So this is why we don't sort of have a notion of like a prime polynomial, but an irreducible polynomial. But you can think of them as generally analogous, right? So the objective is to be given a polynomial and to give back like a list of irreducible polynomials for which their product gives you the thing that you passed in. Okay, when I sent you away last week, I asked, maybe you can think about how you could factor polynomials by exploiting integer factorization. Did anyone sort of figure this out? It's pretty cute. Okay, so suppose you want to factor 9x to the power of 4 minus 1. And you're allowed to evaluate it. And you also are allowed to factor integers. So I evaluate f at 10. I get 89,999. That actually has prime decomposition 7 times 13 times 23 times 43. And I can say, well, at 10 is like 10 minus 3. 7 is 10 minus 3. 13 is 10 plus 3. 23 is 2 times 10 plus 3, and 43 is 4 times 10 plus 3. So like, maybe this is the factorization? Could be. So unfortunately, it's not, right? So you do this, and then you ask if any of these polynomials divides like the thing that you're trying to factor. And if it divides it, great. Divide it, and then try to factor what remains, which is going to be necessarily smaller. If it doesn't work, you don't have to give up. You can just try different pairings or different triplings or different quadruplings. So I say, okay, none of the linear factors worked. What happens if I do 7 times 13? I can get that by doing 100 minus 10 plus 1. That's this, x squared minus x plus 1. But shit, that doesn't divide f. Okay, let's try a different one. 7 times 23. That's 2x squared minus 4x plus 1, evaluated at x equals 10. Damn it, that also doesn't divide f. Okay, what about 7 and 43? That's 301. That's 300 plus 1. This is 3x squared plus 1. And yes, this does divide the original thing. So we have found a factor. So we remove that factor from f, and then like do this again. Okay. So obviously we can get luckier by choosing smaller primes. We can get unluckier by choosing bigger ones. It doesn't matter. Like prime factorization of integers is intractable. It's going to be of no use to us to like reduce the problem of factoring polynomials into an intractable problem. But this was like the first method that was used back in like the 60s for trying to factor, and it will work, and it's kind of cute. Okay, before we talk about like how we're going to factor, and it's probably not the case that I'm going to be able to do the rest, but we still have a little bit of time tomorrow. I want to simplify the problem like a great deal, or as much as I can. So there are various things that we're going to assume that's going to simplify our presentation. So first, notice that I don't care about linear scaling factors. I don't care to distinguish 2x plus 2 from x plus 1. Right? I could always just remove that scaling factor. Both of them are going to have the same roots, for example. Right? The roots of your polynomial are invariant to any type of scaling. Okay, so that's the first thing. I'm going to assume that you've removed whatever you can in terms of like constant scaling factors. And the other nice thing is that any polynomial, okay, so I just said we don't care to distinguish between polynomials that differ by a constant factor. Well, that means if you give me any polynomial, I can multiply by the inverse of the leading coefficient. And what does that leave me with? Well, that leaves me with a polynomial with a unit leading coefficient, which is something that we call monic. So it's going to be really helpful to say, look, let's just assume we're always working with monic polynomials. That is, polynomials with nothing in their leading coefficient, because that will just simplify the presentation. So those are the two things that we're going to assume, that when we're given a polynomial for factoring, that polynomial is primitive. That means we've cleared out any of its content, which I'm going to define, and that it's monic. That after we've cleared out its content, that we're going to further multiply by the inverse of the leading coefficient to make it monic. So making a polynomial monic is easy. When the coefficients are taken from a field, the leading coefficient of a is guaranteed to be invertible, and thereby a times the inverse of the leading coefficient of a will be monic. Right? This will also guarantee that the factorization will be into monic irreducibles. Because if I know that the thing I'm trying to factor has a unit leading term, all of its factors also have to have a leading unit term. Does that sort of make sense? Great, right? That's going to simplify things, because otherwise we need like a standard way of writing a polynomial. Because as soon as you start talking about equivalence classes, it becomes problematic that there's like an infinite amount of ways you can represent the same thing. Right? So there's this word that has very poor definition in math called canonical, to say when there's an equivalence class, this is the thing that we're designating as like the representation for that equivalence class. Right? So 13 is not allowed to exist mod 7, right? Because the canonical representation of 13 mod 7 is 5. The same thing here, I'm saying if you have 2x plus 2, the canonical representation of that is x plus 1. Right? So again, we're always just going to presume the stuff coming in is monic, and that we're factoring into monic irreducibles. So you're going to find these two operators in your Julia code. The first one's for content, and the second one's for the primitive part. The content is easy. This is just the GCD of all of the coefficients. So if you think of this example that I was speaking, this 2x plus 2, right? GCD of the coefficients of that is 2. Right, so this is going to be the thing that allows us to remove the scaling factor. So the content is the GCD of the coefficients. The primitive part of A is it's A divided out by its content. So once we find the primitive part of A, you just multiply by the inverse of the leading coefficient, and boom, you have your canonical representation of that polynomial within our equivalence class. So here's some examples. If you have 6x cubed plus 3x plus 3, its prim part is going to be 2x cubed plus x plus 1, right? Because there's a common factor of 3 in all of the coefficients. So 6 divided by 3 is 2, and then 1, and then 1. And then furthermore, we can take this and just multiply by the inverse of 2. But we need to be working in a residue class of prime characteristic first. Okay, here's a second thing that I want to simplify. So if you have a number that you want to decompose, it's enough to just find, right? So you have like, what's the number here? 2 squared and 3. 12, okay? If you have the number 12, it's enough to find 2 and 3 as the primes that divide it, the only primes that divide it. Because you can just do repeated division on 12 to re-establish what those powers were. Like if I told you the prime factorization of 12 is like 2 and 3, but like I removed all the degrees, you would be like, okay, I can recover the degrees. That's not a big deal. The fact that you found 2 and 3, that was the big deal. We want to do the same type of thing on polynomials. If I so here's a polynomial like x minus 1 cubed, x squared plus x plus 1 squared, x cubed minus 3x minus 1 to the 7th. What I'm trying to say is, okay, I don't really care about those powers yet, right? If I can take A and find that it has irreducible components x minus 1, x squared plus x plus 1, x cubed minus 3x minus 1. That's the hard part. I can easily then just do repeated remaindering to determine the degrees of these. Does that seem sensible? I see a lot of blank stares. Ask a question. Yeah. Okay, well, just to repeat myself, we're going to, these degrees are going to be something we're going to reconstruct at the end. And I'll show you how we're going to get rid of them when we're given a polynomial. Okay, so I have 5 more minutes. I think I will do this. We'll talk about square free, and that's where we'll end. So tomorrow we'll pick up here. Okay, so where were we? Okay. So we're not going to be factoring over Zx. For one, we're going to have to be doing a lot of divisions and GCDs and stuff like that. So the factorization that we're going to be doing is over Zp. And then what we're going to have is a bunch of mathematical statements saying that, look, if you factor a polynomial mod p, that's the same thing as like, how can I put this? Well, it's this statement. Okay, so we'll just read this statement because I think that's the best way to put it, okay? If you have a polynomial with integer coefficients, which has no content, and which is square free. Did I skip that? Okay, so this is a little bit out of order. Which is square free, and it's sort of A factors into these irreducible components. This is saying that if you have the irreducible components and you take their product, and then you do mod p, that's the same thing as like taking all the irreducible components, doing them individually mod p, and like doing that product. So this basically allows us to sort of work in these residue classes and keep separating them. They will say that like, don't worry about working in this residue class because the multiplication property that you need for this to work is true. Right, so this is just a proposition sort of ensuring that everything else that comes subsequent to this is going to be like theoretically sound. Okay, so I'm going to skip a little bit of this. You don't need this, but this is a way that you can work out if a polynomial is irreducible or not, which actually isn't that simple. If I give you an arbitrary polynomial, how can you tell if it has roots or not? Right? You can do it for quadratics, you can do it for cubics, I think you can even do it for quartics. Can you do it for syntax? I forget what the cutoff is. Right? Is it inclusive or exclusive? So, You can't do 5. Okay, so you know the quadratic equation, right? So that tells you explicitly how to get the roots of a quadratic. There is a similar set of equations for cubics and a similar set of equations for quartics, and then it's impossible. It's not that we can't find the equations, it's that it's like provably impossible to produce them. This is sort of like the whole objective of Galois theory, is to like get you to that point where like you can state like the quintics have no generalizable, like have no equation that solves them. So this is just walking you through an example of how you can deduce if a polynomial is irreducible, if that is your interest. If not, you can just skip it. Okay, so square-free polynomials is where I want to finish today. So I'm just going to show you a series of results that are going to be helpful in what I want to do in terms of simplifying our algorithm. So some polynomials will have multiple roots, right? Like x minus 1 cubed. We say that 1 has like multiplicity 3. And I'm saying I don't actually want to like care about degrees yet. So what I want to be able to do is like given an input polynomial, I want to like remove all of the repeated roots so that all is left is like a product of irreducibles of like to the power 1. And how do I do this? Well, there's something called a square-free polynomial. And a square-free polynomial can't have repeated roots. We could call this a repeated root-free polynomial, but notice that like if you have a repeated root, you have a square, right? If you have 7 repeated roots, you have at least 2 of them, right? So saying something is square-free is also saying that it has no repeated factors, right? Because to have 3 repeated factors, you have 2. So these are interesting lemmas. You can all prove these using calculus. They're kind of interesting. A in ZPX is square-free if and only if the GCD of A and A prime is 1. Right, so you can try to prove that. Lemma 2. If A is in ZP and A is equal to this factorization, so each of these F's are, I'm grouping all of the factors into their multiplicities, right? So F1 is the product of all roots of 1 multiplicity. F2 is the product of all roots that have multiplicity 2. F3 is all the roots that have multiplicity 3. So you write A like this. Turns out the GCD of A and A prime gives you this. Right? So it's just all of these powers here are reduced by 1, and F1 is gone. Why is this interesting? Well, notice what happens if I take the GCD of F and F prime. Oh, this is wrong on the left-hand side here. I think I wanted to do this. Frac F for that. Whoops, damn it. Is it this? Yeah, here. Frac. Oh. Okay, great. So if you take F and you divide it by the GCD of F and F prime, what happens? Well, it gets rid of all of the multiplicities. Right? What is left is a polynomial of all of the roots, but like with no multiplicities left. And so it's going to be easier to factor this than it would have been to factor this. But once we have this, we can easily recover all of the degrees here, right? Just by doing repeated remaindering. So you can look at this example. So here's F, x squared plus x plus 1 cubed, x cubed minus 3, x minus 1 squared. That's in Z11. This is their GCD, and this is their division. Right? So their division is like very similar to this factorization, except the powers are gone. So tomorrow, what we're going to do is, given a polynomial which is square-free, produce this factorization. Okay, so maybe you should look over some of this stuff, because tomorrow I'm going to give you the rest of the algorithm. So today, good job. Go home, mull it over a little bit, and I'll see you tomorrow, 1 hour later, across the hall. Any questions from the chat? Okay, you have a good evening too then, chat. I'll talk to you later.